If you search for what is data science, you will find hundreds of answers. Most of them will show you a Venn diagram, 3 overlapping circles, math, coding, and domain knowledge. And somehow, the magic happens in the middle. But here's the problem. That diagram tells you nothing. It does not explain why data science works. It does not explain when it fails. And it definitely does not explain what separates a good data scientist from someone who just runs code. Today, we are going to look at data science the way an economist would, with a skeptic view, focusing on the core aspects and questioning the assumptions that often go unchallenged. Let us start with what most people think data science is. The standard story goes something like this. You have data. You clean it. You explore it. You build a model. The model makes predictions. You deploy it. Done. But this version of data science is incomplete. It skips over all the hard questions. Questions like, why did you choose that model? What assumptions are you making? Is your prediction actually meaningful? These are not minor details. These are the questions that determine whether your analysis is useful or misleading. So what is data science? I think it rests on 4 pillars. And understanding these pillars is what separates someone who uses tools from someone who truly understands what they are doing. The first pillar is probability and statistics. This is the foundation of everything. Every dataset you will ever work with is a sample. It is not the full picture. It is a slice of reality. And the question you are always trying to answer is, what can this slice tell me about the whole? Statistics tells you how confident you should be. It tells you when your sample is too small. Without statistics, you are guessing. You might be guessing with a fancy algorithm, but you are still guessing. Think about it this way. If I flip a coin 10 times and get 7 heads, does that mean the coin is unfair? Most people's intuition says yes, but statistics says not so fast. With only 10 flips, 7 heads is not unusual at all for a fair coin. That same logic applies to every model you build, every pattern you find. The question is always, could this have happened by chance? The second pillar is linear algebra and optimization. This is the engine that powers machine learning. When you train a model, you are solving a math problem. You are searching for the best set of parameters, the ones that minimize some measure of error. Linear algebra gives you the language to express these problems efficiently. Vectors, matrices, transformations. These are not abstract concepts. They are the actual computations happening inside every model you use. When you run a linear regression, you are multiplying matrices. When you train a neural network, you are doing thousands of matrix operations per second. You do not need to be a mathematician, but you do need to understand what these operations mean. Because when your model behaves strangely, and it will, this is where the answer lives. The third pillar is computational thinking. Computational thinking is not about memorizing Python syntax. It is about understanding algorithms, efficiency, scalability, how to take a theoretical idea and make it work on real data at real scale. A model that works perfectly on 10,000 rows might be completely useless on 10 million rows. Not because the theory is wrong, but because the computation does not scale. Understanding time complexity, data structures, and algorithmic design is what lets you bridge the gap between theory and practice. The fourth pillar is causal and inferential reasoning. This is the pillar that most data science education completely ignores, and it might be the most important one. Here is a classic example. Ice cream sales and drowning rates are highly correlated. When ice cream sales go up, drownings go up. Should we ban ice cream to prevent drownings? Obviously not. There is a third variable, temperature. Hot weather causes both. This seems obvious in this example, but in real data science, these hidden variables are everywhere, and they are much harder to spot. Econometrics has spent decades developing tools to handle this problem. Instrumental variables, difference in differences, regression discontinuity, natural experiments. These are methods specifically designed to separate correlation from causation. This channel is about understanding data science, not just using it. In machine learning, the goal is usually prediction. Can I predict the next word? Is this image a cat? But in economics, policy, medicine, and many other fields, prediction isn't enough. We need to ask harder questions. Why did this happen? What caused it? What would change if we intervened? These aren't the same question, and they don't have the same answer. A model can be brilliant at prediction and completely useless for explanation. Accuracy and understanding are not the same thing. For many applications, prediction is enough. But for decisions that affect people's lives, like hiring, lending, medical treatment, or public policy, you need more than a good guess. You need to know why. You need causality. And that is what this channel is about, not just how to use the tools. We are going to build your theoretical foundation from the ground up. We will start with probability and statistics. We will cover distributions, hypothesis testing, and the central limit theorem. We will dive deep into linear regression, not just how to run it, but why it works and when it breaks. Then we will move into the topics that most data science channels skip entirely: causal inference. Every video will follow the same philosophy. Start with the intuition, build up the math, and connect it back to real problems. If you are a data science student, this channel will give you the theoretical depth that most courses skip. If you are a working data scientist, this will sharpen your thinking and help you diagnose problems faster. Thanks for watching. If you found this helpful, hit the like button. And if you have a topic you want me to cover, drop it in the comments.